So in this unit 4, you are going to learn about gravity. Again, you've learned about gravity already. You learn about projectiles and satellites. So in the first lesson, what we are going to cover in this video the universal law of gravitation or the universal law of gravity, the inverse square law, that is how does gravity or the force of gravity, how does that vary with distance? We're going to talk about weight and weightlessness, and then we'll talk about universal gravitation. So, the legend of the falling apple. So, there's this story that Newton was not the first to discover gravity. Newton discovered that gravity is universal. Newton was sitting under an apple tree and realized that the force of gravity between the earth and the apple is the same as that between moons and planets. So actually, he was sitting under a tree and he saw an apple falling. And so he asked himself, why is the apple falling towards the earth? So that question is what actually sparked the thinking and the critical thinking of Newton. In ancient times, you had other scientists like Aristotle and others that believed that stars, planets, and the moon they moved in divine circles from forces of the earth. We now know that the moon falls around the earth. Have you ever asked yourself the question that each time we talk about the planets moving around the sun, we talk about the moon going around the earth? Have you ever asked about yourself about the question that keeps those objects moving in those orbits? What is keeping the earth on its orbit? What force is keeping the earth on its orbit such that it moves around the sun every 365 and one quarter day? What is keeping the moon to keep moving around the earth? Right? That force is what we call the force of gravity. Okay? The moon maintains a tangential velocity which ensures a nearly circular path around the earth. So, what is tangential velocity? Have you ever tried to hold an object and you spin it using a rope? Let's say you tie an object to one end of a rope and you're spinning that in a circle. If you keep spinning that in a circle and you suddenly allow the rope, you will realize that the rope is going to travel in a straight line. That path is what we call a tangential path. Okay. So, the universal law of gravitation or the universal law of gravity. So, this was formulated by Newton. Everybody in the universe attracts every other body with a mutually attracting force. For two bodies, this force is directly proportional to the product of their masses and inversely proportional to the square of their separating distance. So, what Newton formulated actually is that if you take the force, you multiply that by a constant. This constant here is called a gravitational constant. You multiply that by the two masses. For example, if you want to calculate the gravitation or the force of gravity between the earth and the moon, it means that this m1 is going to be the mass of the earth and the m2 is going to be the mass of the moon, or vice versa. Now, this d is going to be the separation distance between the earth and the moon. And so this big G is a value that you're always given. They always give it to you if you are calculating in any problem. Newton discovered that gravity is universal. So again, remember we've learned in the previous unit that if you drop a piece of stone and a piece of feather in a vacuum such that the only force acting on those objects is the force of gravity, then they will all fall to the ground at the same time. That is the idea behind the universality of the force of gravity. It's the same everywhere. Okay? Every mass pulls on every other mass. every mass pulls on every other mass. So when as you guys are sitting in class, you are pulling on each other. Okay. So let's check this out. Newton's most celebrated synthesis is the earthly and heavenly laws. This synthesis provides hope that other natural phenomena follow universal laws and ushered in the age of enlightenment. Newton's law of gravity, I've already given you that formula, okay? The greater m1 and m2, the greater the force of gravity. So obviously, the force of gravity between two students in a class, right, is not the same force of gravity between the Mars and the moon. Why? Because the Mars is more massive and the moon is more massive. So when two objects have a very great mass, their force of gravity, right, will be stronger. The greater the distance of separation d, the weaker the force. So if the two objects are separated 2,000 miles away, obviously the force of gravity or the pulling force between one another is going to be weaker compared to if they are, let's say, 1 mile away. So that is what leads us to the inverse square law. Inverse square law because it relates the intensity of an effect to the inverse square of the distance. So what that means is the strength of the force is going to vary inversely with the square of the distance, right? You see, inversely, the way we write that in math is 1 over the distance square, right? So the greater the distance from the Earth, the less the gravitational force on that object. The greater the distance from the Earth, the less the gravitational force on that object. No matter how great the distance, gravity approaches but never reaches zero. So imagine that you have in fact, you have an infinitely long distance that is separating two objects. Yes, the gravitational force is going to be very weak, very small, but it will never be zero so long as the object has mass. So again, this is a diagram that really represents the inverse square law. As you can see, 1 unit, 2 unit, 3 unit, 4 units. You see the distance is actually approaching, and so you can actually see that for the first unit you only had one square, right? Now for the second unit, you now have that one square divided into four. So in that second one, you now have four boxes. You now see that it is two squared. By the time you reach 9, you see that same box is now divided into 9 small boxes. So you have 3 squared, that gives you 9. So now guess, for 4, how many square will you have? Normally, if you divide it, it's supposed to give you 16 because it's 4 squared. And so that is a graph that shows that as the distance is increasing between the two objects, right, the force is actually dropping. That's a relationship. So when the distance is almost zero at this top right here, you can see the force is actually very high. The force of gravity between two planets depends on their A. Masses and distance apart, B. Planetary atmosphere, C. Rotational motion, D. All of the above. Obviously, it depends on the masses and distance apart because from the formula, we say that F is equal to G. This is a constant times mass 1 times mass 2 divided by the square of their separation. D is their separation, so you make sure you square that. So it depends on the masses of the object and the square of their separation. If the masses of two planets are each somehow double, the force of gravity between them will be. If the masses are double, take note. If the masses between two planets are somehow double, the force of gravity will quadruple. Why does it quadruple? Because when you double the mass, there are two masses here. So you double the first one, you double the other one. So it will be like kind of a double times a double. That's why it gives you a quadruple. If the mass of one planet is somehow double, the force of gravity will double, okay? Because it's just one mass in this case that you're doubling. You're not doubling the two, you're doubling just one. So now I remember I told you that G is a constant. So G is a proportionality constant in Newton's law of gravity. G has the same magnitude as the gravitational force between two 1 kilogram masses that are 1 meter apart. So the value will always be given to you, and that value here is 6.67 times 10 to the 11 Newton meter square per kilogram square. Okay. The universal gravitational constant G, which link force to mass and distance, is similar to the constant pi. It's just a constant. Just as pi relates the circumference of a circle to its diameter, G relates the mass and the distance. So now let's look at weight and weightlessness. What is weight? Do you guys remember? It is a force exerted against a supporting floor or weighing scale. Okay, your weight acts downward. Now, what is weightlessness now? It's a condition where a support force is lacking, free fall, right? You feel like there's no support force. Your legs are not touching the ground. That condition is called weightlessness. Now we look at examples. Examples of weightlessness. You have no support force. An astronaut is weightless because he or she is not supported by anything. The body responds as if gravity forces were absent, and this gives the sensation of weightlessness. That's why you look at them sometimes in space, it gives that feeling that they're flying in the air, right? They're flying because there's no support force. They're not touching any surface. They can't press on any surface. So you have a normal weight. The first situation is a normal weight, okay? Then this one, you have greater than normal weight. You see the arrow is pointing upward. So by in this case, you have less than normal weight, and in this case, you talk about weightlessness now. Because remember, there's no rope. There's a rope here, right? So when you are in a lift, for example, when you're in a lift, let's say you take the elevator, when the elevator is not moving, you feel like that is normal weight right there. Okay. Now, when the elevator start going up, you feel like your weight, you're feeling like greater than your normal weight. Now, when the elevator is going down, right, you feel like less than your normal weight. But by the time the rope that pulls the elevator cuts, you feel like you don't have any weight, zero weight. When an elevator accelerates upward, your weight reading on the scale is, we said that's greater than your normal weight when you have the elevator accelerating upward. Now, when the elevator is accelerating downward, right, you feel like less, and then the next one, when the elevator cable breaks, again you feel zero weight in the weightlessness. If you weigh yourself in an elevator, you will weigh more than the elevator. Moves upward, moves downward, accelerate upward. If you weigh yourself in the elevator, you will weigh more when it accelerates upward. All right, so that's that for this section. Make sure you copy your note and then you use it to do your head puzzle.